So it's one of the first questions people ask of us of why should I buy a foam interior for a case shell that sometimes and very often exceeds the cost of the case shell itself? Because I've been online, I've seen that the factory pluck foam kit that comes with the case is just a small fraction, maybe 20, 30, 40, 50 or $100, and that looks like a perfectly acceptable solution. Why shouldn't I use it? Well, let's get into sort of our back room and have an understanding of why this very often is not a good solution. Every foam that you find out there has a sweet spot. It has a given density of material that in turn lets you be able to load it in a certain load range. That is, if you start with a very, very light load on the foam, there's no cushioning whatever. That even in a drop situation, that very light load doesn't cause the foam to compress. So you've got exactly the same cushioning properties as you would have if you encase that in Quikrete. If you lock it in with cement. So we've got to have enough weight per square inch to cause a little bit of compression during a drop event. So we go to what in packaging terminology is the U-shaped curve. There's a certain point where you load that foam enough and you start to get a bit of deflection during a certain height of drop, and energy starts to be absorbed and the product is protected from some of that energy. And if we gradually increase that load and go through further testing, we get to the bottom of the U-shaped curve more or less, where we're getting really, really good protection. But then we get to the point of taking a ride in Grandpa's old station wagon with all the kids in the back and the suspension's mashed down flat, and we mash that foam flat on the initial load or the very early part of the drop, and there's no absorption of energy, so the U-shaped curve comes back up. So we want to design toward the middle of that curve. Well, you buy the pluck foam kit, you're buying one type of foam. You put something like a desktop CPU into that. Well, on the large surface of the desktop CPU, you may have 400 inches of bearing area and 40 pounds of product. So you have a very low weight per square inch. It's 5 inches wide on the other end. You have less than 1/10 of that, so you have 10 times the load factor. In our shop, our designers will go to work for you, and they'll do one of two things. They'll use a lighter density foam on those wider surfaces, or they will configure the foam so there's a progressive input. You're probably familiar with the so-called convoluted foam. Most people call it egg crate foam, the foam with the tips. One of the things that accomplishes is to respond better to something with a lighter load, because you're first engaging the tips of that foam so it can absorb energy at very low load. Sometimes we build in handholds or literally just V-shaped notches to do the same thing on the ends or the sides. In other situations, we simply go to higher density of foam, because that higher density foam wears better. So as you take the item in and out, you're not generating as much particulate matter, and you're increasing the life of the product. There are other times that we, with really delicate equipment, that we may literally work in a fairly high density material, but at certain key points, we have some very high energy absorbing isometric foams that are very good at absorbing vibration as well. And those foams are normally what people think of when you think of memory foam. That is, they are very slow to compress and slow to rebound. So the offset there is that they're soft, so we need to compensate for that in the package design so you don't tear things up as you take things in and out. So hence, we often work them into the design so that the more durable foam is in contact with your unit, transmitting that shock load to the memory foam or the isometric foam to absorb shock and vibration. In turn, there are different foam families, and each of them have their strengths and weaknesses. The big three are the polyurethane families, and that is what your plug foam is made from. This is a process of bringing a couple chemicals together with catalysts, and you're able to control density, wall thickness, and the amount of air bubble, or excuse me, the amount of porosity in between the walls that actually form the bubbles of the foam. So you can have some foam that has no air trapped in it, whatever. You can have other grades of that material that have very little air movement in between each of those pores of foam. So that which means that you, if you have the material that has very easy air movement, there's no shock absorber effect. When it's impacted, it collapses very quickly, bounces back very quickly, and transmits a lot of energy. So ideally, we want that happy medium where the air movement slows that compression and slows the rebound, so there's less energy transfer. Now, the urethane foams used to be a standard that dominated our world. They were much less expensive to make. Unfortunately, over the years, we've discovered that some of the chemicals involved are of concern for environmental and ozone reasons. To replace those has driven up the cost of that material, and as well, it's a fairly unfriendly material to dispose of. But it has the properties of being able to tear easy, and to be able to do the kind of die cutting fabrication that is necessary to create the so-called plug foam. So it's still used a lot in that application, but it is neither durable, it is not a product that you'd be proud of to know what's going in the waste stream and you get rid of it. In turn, the new kids on the block, more or less, are the wide variation now of polyethylene foams that are available. For years and years, we had extruded versions of that material that were relatively coarse porosity. There were some trade names, Ethafoam, etc., that you may have ran across. These are exactly that, extruded in a plank. When they're extruded, you have a skin on the surface, so it looks very much like bread. The skin is equal to the crust, and then you have the porous portion in between. Sometimes we use that skin to advantage to, again, increase durability, minimize moisture absorption if that's an issue, and for appearance sake. For a long time, we had a much more expensive version of the polyethylene foams. There was a much smaller cell structure, more attractive, less wear, and this is called cross-linked, where you literally irradiated blocks of the extruded foam, and the radiation punctured the bubbles. They popped and made smaller bubbles, so you had a much finer cell texture. And in turn, you could do higher density versions of that, so that we could get up into really high weight per square inch if we need to. So sometimes those are the materials that you would see that are on at the base of a unit that weighs several hundred or even thousands of pounds. It needs, where it's trapped under a load spreader to give from spring or some cushioning capabilities. So in turn now, to our delight, there are some folks that have pioneered the development of radioactive ways of achieving this. None of the foam was radioactive, but you were creating a hazard of moving those radioactive sources in and out of a production environment, and potentially, if bad things happened, exposure to people in that manufacturing environment. The other aspect as well was those earlier versions of the extruded foam were often done with yielded chemicals that were flammable. And the newer versions of the cross-link foam eliminate that. So there was even a point where the U.S. Navy established some of its own standards for foams that that had none of the flammable content. And by and large, a lot of that has been switched over now. With the cross-link foams, we completely eliminate that. A much wider color selection and a much more attractive surface, much less foam debris generated as products wear or are pulled in and out. So again, to recap, our designers look first at simply the protection issues. What can we do to based on either data that you have about the fragility of your product, or data that we can draw on from a variety of testing that's been done by military and civilian folks to validate what's the typical fragility of this range of product. We know, for example, that something's been designed to be that's relatively, say, under 10 pounds, under the size of a toaster that people are handling. We know that had to be designed so that if it falls off a desk or a table, that very rarely something's going to happen to it. So that lets us know a G-frame reference to design toward. Similarly, a benchtop instrument that was never designed to be carried around in the field may have been designed with a much lower threshold, knowing that they could cut down on the cost of the instrument and the complexity of it by not designing it to be as robust, spending a lot on packaging to get it there, and knowing that it's only occasionally going to need to be moved or moved back for calibration. So we do a lot of work for people that have to, for one reason or another, move that equipment around.